If Proxima Centauri were anywhere else, no one would have ever heard of it. It is a star so insignificant that even finding it can be tricky for your average stargazer. Like 3 out of every 4 stars in our galaxy, it is a red dwarf. A small, cool, flickering ember of a star that, thanks to its efficient fuel consumption, will continue to burn low and quiet for trillions of years, long after our more wasteful sun has sputtered out and died. Red dwarfs are indeed small, but Proxima Centauri is small even for them. Just an eighth the sun's mass, and a mere 7% its diameter. If we were looking at it, it wouldn't appear much larger than Jupiter, despite being over 130 times heavier. But where Proxima Centauri's triviality truly awes is in its brightness, or lack thereof. It is barely 1/600th as bright as the sun, the stellar equivalent of a guttering candle in the night. The reason Proxima Centauri inspires our species' interest is in its name, Proxima, which is Latin for nearest. At this particular moment in time, Proxima Centauri happens to be the nearest star to our own sun, a mere 4.25 light-years, or, if you prefer, just 6,800 times the distance to Pluto. It wasn't in the past and won't be in the future, stars being the fickle, hurrying things that they are, but right now it is the closest we have to a stepping stone to the Milky Way, and so has served as the inspiration for 1,000 dreams of cosmic voyages. But Proxima is not alone. It is the outermost of a triple star system called Alpha Centauri, and it is its 2 larger, more sun-like brothers, called Alpha Centauri A and B, that have traditionally drawn the attention of futurists and science fiction writers. But all that could be about to change, because astronomers at the European Southern Observatory have just announced the discovery of a planet around Proxima Centauri, one that might, just might, be a home to life. Finding planets around other stars is not new, even potentially habitable planets. Thanks to Kepler, a NASA space telescope launched in 2009 specifically to locate prospective other Earths, we found at least 7 more to date, a number certain to grow in future. But the fact that this possible stellar oasis is so close to Earth, a paltry 40 trillion kilometers, has crystallized the minds of wannabe interstellar explorers. What was once mere fantasy is now an observable fact, something that can be studied, measured, and probed. Proxima B, as its discoverers call it, is the first potentially habitable planet found close enough to the Earth for its atmosphere and composition to be observable. In a comparatively short time, say a decade, when the next generation of telescopes comes online, we will have a picture of this world, be it barren moonscape or verdant paradise, that will be as detailed as those we held of the planets in our own solar system before the first robotic explorers reached them. But the more audacious dream even bigger. Even before the planet was announced, Russian tycoon Yuri Milner announced Breakthrough Starshot, a project aimed at reaching Alpha Centauri within just 20 years. For comparison, the New Horizons mission to Pluto, which, remember, is 6,800 times closer than Proxima, took 9 years. Any journey to Proxima would require a quantum leap in propulsion technology. The proposed method involves launching a fleet of 1,000 insect-sized robotic spacecraft equipped with light sails, which would then catch the light of a gigawatt laser and ride it to speeds approaching that of light. It's not exactly a proven concept as of yet, but before now, any thoughts of a destination had been pure guesswork. Now they have somewhere to go. So assuming Milner's armada of micro-Magellans actually do reach Proxima B, what would they see? What would it be like? Frustratingly, beyond the fact that it exists, we know very little about this strange new world. Proxima Centauri is believed to be roughly the same age as our Sun, meaning Proxima B is likely about as old as Earth, give or take 1 billion years. But as to crucial questions like its size and composition, there is little we can say for certain. This is due to the method used to locate it. Most potentially habitable planets have been found using the so-called transit method, watching a star until the shadow of a planet crosses its disk. This allows you to measure not only the planet's mass and orbital period, but also its diameter, and, if you're very lucky, perhaps even the elements in its atmosphere. Problem is, for transits to happen, the star has to be facing the Earth side on, and most of them aren't, meaning transits require exhaustive surveys of vast numbers of stars to locate. To expect any one specific star to have a transiting planet is to tempt fate rather rashly, and indeed Proxima's planet only has a 1% chance of transiting it. To find it, astronomers at the European Southern Observatory employed a more old-fashioned brute force method known as radial velocity detection. This is the same method used to locate the first planet around a Sun-like star back in 1995. I've covered the technique in more detail in earlier videos, but in short, radial velocity involves measuring how fast a star is wobbling in response to the tug of an orbiting planet. Once you observe the star's wobble, you can get a rough estimate of the planet's mass and distance from its star. This method is particularly suited to small red dwarf stars because small stars are larger in proportion to their orbiting planets and so show off more obvious wobbles than larger ones. As of now, we know that Proxima B is at least 1.3 times the mass of Earth, has a 90% chance of being less than 3 times Earth mass, and a 95% chance of being less than 5 times its mass. Its orbit lies 7.3 million kilometers away from Proxima. 7.3 million kilometers may seem like a lot, but consider Earth is 150 million kilometers away from the Sun, while barren, scorched Mercury is 58 million kilometers away. But wait, I hear you cry. How could Proxima B boast any kind of life at such a close distance to its star? The answer lies in that most spectacular fact about Proxima Centauri: its dimness. Proxima is so much dimmer than our Sun that its habitable zone, or the region around it at which liquid water would exist, lies between 6.3 and 12.2 million kilometers. This would place Proxima B somewhere near the inner edge. It's important at this point to clarify exactly what potentially habitable means. Our solar system contains 3 planets within our star's habitable zone, and if they called themselves sisters, people would ask if they were adopted. Mars is a frozen, irradiated desert with daytime summer temperatures comparable to Antarctica, while Venus's nightmare hellscape, with its sulfuric acid clouds and lead-melting temperatures, defies any earthly comparison. Location is only a first step to habitability, and a whole range of lucky accidents, such as impacts, encounters with other stars, shifts in orbit, and atmospheric composition, ultimately contribute whether a planet attains the perfect balance to support life. The first such accident is its mass. Proxima B's probable mass range of between 1.3 and 5 times Earth makes it a super-Earth, a mysterious class of objects that don't exist in our solar system but appear very common elsewhere. A planet is referred to as a super-Earth if its mass is between 1 and 10 times that of the Earth. It's a fairly arbitrary definition, and the precise line between a rocky planet like Earth and a gassy planet like Neptune, which is 17 times Earth's mass, is still not known. No one seriously believes that life could exist on a Neptune-type planet, whose atmospheres are so vast and thick that they mostly consist of a superheated soup of liquid ammonia. So it would behoove Proxima B to have a mass on the lower range. Luckily, that seems likely. Even so, the relationship between a planet's size and the density of its atmosphere is not clear-cut. Venus is smaller than Earth, but its atmosphere is 100 times denser, while Mars's atmosphere is far thinner than it would be if due to gravity alone. Composition of a planet's atmosphere also matters. Venus's average surface temperature is 462 degrees Celsius, but its permanent veil of sulfuric acid clouds reflects the vast majority of sunlight hitting it, meaning that even given its closer distance to the Sun, it should be fairly temperate. The reason Venus is just slightly more hospitable than the inside of a nuclear reactor is because its atmosphere is composed of 95% carbon dioxide, which creates a runaway greenhouse effect that sends its temperatures soaring. The second, and in many ways more intriguing accident to befall Proxima B, is its orbit. Proxima B's orbital period, or year, is just 11.2 days, and knowing that, with a shot of Kepler's third law, we can deduce that it must be 7.3 million kilometers away from Proxima. There is more to orbit than just distance, however. One crucial element of Proxima B's orbit we have yet to learn is its inclination, or how tilted it is relative to Proxima's equator. How tilted a planet's orbit is determines how it makes its star wobble, and thus, once we know Proxima B's precise inclination, we can filter out the noise from its radial velocity results and learn exactly how big it really is. A second crucial element currently unknown is its eccentricity, which is how circular or stretched out a planet's orbit is. This is crucial because Proxima B is close enough to its star to be in a condition known as tide lock, in which the gravitational pull of its star lassos it so that its rotational period, or day, is a precise fraction of its orbital period. In our solar system, the two most famous examples of tide lock are the planet Mercury, which spins 3 times for every 2 times it goes around the Sun, a so-called 2-3 resonance, and our own Moon, which spins once for every orbit around the Earth, a 1-to-1 resonance, also known as synchronous rotation. If a planet's orbit is stretched, then it will likely fall into a 2-3 resonance. If it is nearly circular, then it will fall into synchronous rotation. For Proxima B, each of these 2 outcomes would produce a very different and very alien world. Have you ever noticed that you only ever see one side of the Moon? No matter when you look up at it, day or night, regardless of the time of year, it always shows the same familiar patterns. The man in the moon with his permanent gasp of surprise. Knowing what we know about our planet, this can seem odd. After all, our planet spins every day. Why not the Moon? Truth is, the Moon does spin. It just spins once for every orbit it makes around the Earth. You can see this if you move your finger around your head, but hold it so that it is always pointing toward you. You will see that to do so, you have to rotate your wrist. But our Moon still orbits the Sun with us. Each side still gets a fair share of sunlight. The dark side of the Moon is only dark in the sense that we can't see it, not dark in the literal sense. But for a planet in synchronous rotation around a star, the sense would be very literal indeed. If Proxima B orbited its star the way the Moon orbits the Earth, spinning once for every orbit around it, one side would be in permanent darkness, the other in permanent light. The Sun would neither rise nor set, but hang motionless in the sky. Midnight, twilight, and noon would not be times on such a world, but places you could visit. There would be no count of days, since days would not exist. Only one eternal day region and one eternal night region separated by a realm of twilight. The shadows cast by mountains would be permanent features, creating islands of night where plants could not grow. Assuming it were tilted on its axis like Earth, Proxima B might see its sun move across the sky from solstice to equinox and back again over its 11-day year, but it might lie too close to its star even for that. Given that its distance from its star also likely precludes formation of large satellites like the Moon, any sentient life forms on the planet would have to rely on the stars of the night side to tell the time. As I noted in previous videos, many earlier speculations about planets in synchronous rotation around their stars suggested they were completely inhospitable to life, since their atmospheres would not effectively transfer heat from one side to the other, and would either freeze out over the night side or need to be so thick that no sunlight would ever reach the surface. However, more recent models have shown that an atmosphere only as thick as our own would have no problem circulating heat from the day to the night side, and that a synchronously rotating planet could have a fairly clement, if very strange, climate. The ESO have produced a climate model for a synchronously rotating Proxima B, assuming an Earth-like atmosphere and ocean. At the very tip of the sun-facing side, noon, if you will, average temperatures are similar to those found in the Sahara, while the twilight region will be home to the outer edge of a vast, world-spanning ice cap that would smother the entire night side. A night cap, as it were. Between these two regions, however, would lie a temperate afternoon region where life could flourish. Given that Proxima B is larger than Earth, it may be home to as much habitable space as our own planet. The second scenario, a Mercury-like 2-3 resonance, perhaps surprisingly, produce an even harsher environment, with only an equatorial belt remaining permanently ice-free. If, however, Proxima B's atmosphere contains several times more carbon dioxide than Earth's, it could produce a relatively clement, Earth-like environment. On a planet with a 2-3 resonant orbit, each hemisphere would alternately experience one whole 11-day year of daylight, followed by 11 days of night. One wonders at the survival strategies of any creatures on such a world. Do they go into hibernation to conserve energy during the sunless times? Are they attuned to their longer cycle, and thus see their 22 days as no different from our 24 hours? For many years it was assumed that life could never form on the planet tidally locked to its star, because it wouldn't be rotating fast enough to generate a magnetic field. Deep in our planet's molten outer core, a spinning ocean of liquid iron creates an electromagnetic envelope that surrounds the Earth like a bubble thousands of kilometers thick. The bubble acts like a force field, catching harmful emissions from the sun and channeling them to the poles, where they discharge as aurorae. Without the shield's protection, the Sun's periodic expulsions of plasma, known as coronal mass ejections, would burn off our ozone layer, eventually completely irradiating our planet and leaving its land surface as barren as the Moon. For decades, scientific consensus was that the iron in our core was kept spinning by Earth's rotation, and that planets that rotated more slowly could not get their core spinning quickly enough. That would be a particular problem for any planet around Proxima Centauri, which is known to flare and rage far more frequently than our own Sun. Thankfully, more recent models have suggested that the true driver for the core's motion is convection, the movement of material from the hot core of a planet to its surface, where it cools, flows outwards, and then falls back to the core again, creating vast cells that keep the planet's interior in constant but slow motion. On Earth, these cells act like conveyor belts that gradually pull our continents across the globe, all the while generating earthquakes and volcanoes. A study by Professor Roy Brown of the University of Washington concluded that this motion is more than sufficient to generate a magnetic field strong enough to protect the world from its star's tantrums. As noted in the previous video, red dwarfs take far longer to settle down into their stable main sequence life than larger stars do, and are prone to wild, explosive childhoods that would bake any nascent planet before it could develop life. If Earth had formed in a similar position to Proxima B, it would have lost all its water early in its development, and would have evolved into another Venus, a parched, smothered inferno. But there are ways out of this fate. If Proxima Centauri calmed down quickly enough water might have been preserved on Proxima B to stabilize its climate. Alternatively, we now know that many planets formed farther out from their current locations before spiraling inward. If Proxima B had formed a safe distance away from its star, and then migrated inward later on, it could have retained whatever water it had when it formed. So let's assume that Proxima B, like our own Earth, made all the right turns on the highway to life, and now supports a verdant, sprawling ecosphere of infinite diversity. What would it look like? Well, chances are, not anything you've ever seen. For instance, the word verdant, a common enough word to describe a plethora of thriving plant life, is very likely not the word to describe what we find on Proxima. Verdant means green, and green is exactly not what one would expect life on Proxima B to be. You wouldn't think that "why is the grass green?" is an astronomical question, but it makes sense when you realize that a plant is basically a starlight-eating machine. Plants have evolved to eat the light coming specifically from our star, the Sun, and our star produces light in a very specific way. Without going into too much detail, the Sun's light can be broadly defined as a stew of low-energy red light, high-energy blue light, and mid-range green light. Red light particles, called photons, have less energy, but the Sun produces lots of them. Blue photons are rarer, but crackling with tasty energy. The middling green light, however, is neither energetic enough or common enough to interest a plant, so it reflects it out, focusing on the photons it wants. But a red dwarf star is very different from our Sun. As you can probably guess, most of the light visible to us coming from it would be low-energy red light, while high-energy blue and green photons would be rare as gold dust for any plant life. Most of the light emitted by a red dwarf would be low-frequency infrared light, invisible to our eyes. Therefore, it is likely that any plants that evolve on such a world would suck up every available photon, and not be as wasteful as the spoiled plants on our world. And when an object absorbs every visible color, reflecting nothing back, we call the result black. So perhaps instead of verdant, a more appropriate French word for this planet's biosphere might be noir. Finally, there is one element of Proxima B's location that, while not necessarily fatal, will nonetheless ensure that life on the planet stays exciting. No planet or moon has an orbit that is perfectly circular. Sometimes they come closer to their primary, sometimes they move farther away. When they move closer, the gravity of their primary tugs at them a little harder, distending its shape. This is how the moon raises tides on Earth. Jupiter raises tides on its moon Io so extreme that its surface is repeatedly tugged by as much as 100 meters. This constant kneading stirs and roils Io's insides, causing them to spew outward in vast volcanic eruptions. At any one moment, you can expect at least 2 volcanoes to be erupting on the surface of Io. And Jupiter is just a planet. What of a star 100 times heavier? Proxima B is likely close enough to its star for it to raise gargantuan tides. Would they tear the surface apart in a raging firestorm? Would they raise waves 1,000 feet high? Perhaps not. It may be just far enough away, or its orbit may be circular enough, the tidal effects would be relatively modest. But even so, you'd have to watch your step. The importance of Proxima B to the human race cannot be overstated. A potentially habitable planet has been found around our nearest star, close enough to be seen as a unique living world, close enough to visit, or even perhaps contact. But there is a far more immediate and selfish reason for our species to be thankful for Proxima B. Astronomers believe that our world has perhaps 600 million years of habitability left before our sun decides it's had enough of us. Proxima B, whatever its current condition, will still be in that condition 600 million, and indeed 600 billion years from now. If our species is to survive long term, it must eventually lay claim to Proxima B, or somewhere very like it, as our new home.